Good afternoon, everybody, and welcome back. It's time for the application session. As starters, I'd like to introduce Leonardo Ribeiro. He's going to speak about the use of both Saber and Kyber in mobile devices. Go ahead, Leonardo. Go ahead, Leonardo.
Okay, are you seeing me? Are you see the presentation?
Yes.
Okay, let's start. Everybody, good afternoon. My name is Leonardo Ribeiro. I'm a researcher from Federal University of Pernambuco, Brazil. Now I'm going to show you some results that we have found while testing Saber and Kyber performance. So, let's show you the main topics of this presentation. And first of all, we are going to show you how we have done the tests of Saber and Kyber code. After that, we are going to show you the performance test data that we have found for Saber. Then after, for Kyber, we have tested in architectures X4 and ARM architectures, both for Saber and Kyber. So let's talk about the first topic. And there is a picture that briefly summarizes how we have tested Saber and Kyber. First of all, we created a Java code to do the performance tests. So we decided to create a Java code because we needed to test the Saber and Kyber in mobile devices. So with this code created, we used a Java native interface to create header C codes. So because Saber and Kyber code is built in C language, so we needed to use a Java native interface. And we also created a performance test code in C, so it could be used to communicate with Saber Kyber code and the files that were created through Java native interface. After the creation of these files, we compiled these code files, and for x64 architecture, we used GCC compiler, and for mobile devices, we used NDK compiler that is used in Android device. So with this file created, can.so, we had the opportunity, so we could test the Java code. After that, we take the Java code and compile it referencing to this file can.so, and then after that, the class that were created, we had the opportunity to run the tests, the performance tests. We have done the tests for the first test we have done to test the round 2 code of Saber and Kyber, and the second test that we have done, it was to test round 3 code for both Saber and Kyber code. So after that, we run the tests and we collect the profiling data. And so how were the tests done? Using standard versions of both Saber and Kyber. And how was the test done? First of all, we had the input. As input, we had a key session object with 128 bytes, and for output, we had the profiling data that we needed to evaluate Saber and Kyber performance. So how we did the code? The code was done in 3 steps. The first step, we had to call the key pair function from both Saber and Kyber code. And then after call the keeper function, we call it the encryption function using the public key created the last step. And after that, we use it, the decryption function, so we could decrypt the data and check if it was okay. And we for the test we need to use padding because the input data was not multiple of block size of each Kyber and Saber algorithm. So the algorithm versions evaluated for us was for Kyber we used the 1024 version, and for Saber we used the Fire Saber version. Both of them use security level 5. So that was the versions that we used for testing. And the device that we used for testing Saber was a mobile device based in ARM architecture version 8, and we used a PC for testing x64 architecture. So as I said, we used security level Party Saber for testing Saber. And what was the data that was collected? While testing Sabers, we found that we collected the round 2 data. We have found that the round 2 data was better than round 3 data because the performance was better. You can see through this slide that in green letters that you can see that the round 2 was better than round 3 code performance tests. It was done for x64 architecture, and for ARM architecture we have also done the test for round 2 and round 3 code. So we found out that round 2 had better performance compared to round 2 code. And we also tested Saber, and we have found some bottlenecks on the code. While testing round 2 code, we have found that while executing key generation functions, we have found that this function matrix vector mode was the function with the highest consumption. And we also have tested round 2 code, and we also have found that matrix vector function was also the function with the highest consumption. And we did it for encryption. Decryption, we have found for decryption that matrix vector mode function was the bottleneck, and for decryption we have found the inner prod function is the bottleneck for consumption of the code. So it was for x64 architecture. And for ARM architecture, we have also done the same tests. We have found the same functions, but we can see through the slides that the values that were found are more balanced compared to the values that were found while testing x64 architecture. So that this is a picture showing the comparing and the tests for x4 and ARM architectures. So for x64 architecture we have used the Linux, and for ARM architecture we have used Samsung Galaxy X20. We have found that Linux had worse results compared to X20. And for ARM and for round 3 code, we have also found that Linux had worse performance compared to S20, but we have found that the S20 had better performance times compared to round 3 tests on Saber. So that's it for Saber. We also try to do some improvements in code, in Saber code. We try to use shift operations instead of division by power of 2 on this function Karatsuba simple. We had found that with these changes, we had found an improvement of 3.26% compared to round 2 original code. So these improvements are not conclusive. Maybe someone from Saber team needs to find out if it really was a real improvement or not. And now we are going to talk about Kyber tests. We have used the same device. We have used a mobile device on ARM version 8 to test ARM architecture in PC to test x64 architecture. And the security level used to test Kyber was this one 1024. So for Kyber, we have found some different results. For example, for round 2 code tests, we have found that Galaxy had worse results compared to Linux in some points of the tests, and for round 3, we have found that Linux had worse results compared to Samsung Galaxy S20. So compare round 3 and round 2 code, we have found improvements in ARM architectures. So compare now Samsung Galaxy S20, compare round 2, round 3 tests, we can find that we have improvements in round 3 comparing to round 2. And for Linux, we had some results that are different from. So the round 3 results were worse compared to round 2, while testing the Kyber in Linux. So there is a pie chart that you can find out that the part of the code that had the highest consumption was in the encryption, and the lowest was in the decryption. While we have tested Kyber code. So that's the conclusions of Kyber tests. Average execution time for Linux was increased. Average execution time for Android was reduced, and top values were kept. So we have concluded that Kyber was optimized for ARM architecture in NIST submission. So we also tried to find some code improvements in Kyber, but we haven't found. So we tried the same idea to change division of power of 2 to shift operations, but there is no effect in the change. So we also tried to use a different version of Kyber. It's called the 90s variant, and then we have found out some improvements. And we have found that we had better times for decryption, worse time for key pair generation and encryption. And that's the graph that we have found for while in testing 90s version of Kyber, and you can find out that 19th was worse than compared to 1924 version of Kyber. So that's it that we have. So Is there any questions about the results that we have found?
Hi, there's one question on Slack and a few questions in Blue Jeans, but we've run out of time, so you'll need to answer those in the by typing in the answers.
Okay.
So thank you for that talk. The next we're going to hear from Aurélien Greuet. He's going to speak about smart cards and post-quantum crypto.
Hi everyone, can you hear me? Can you see the slides?
Yes.
Yes, okay, thank you, great. Okay, so my name is Aurélien Greuet, and the goal of my talk is to explain why implementing post-quantum crypto on smart card is not an easy task, and to suggest solutions to make the transition easier. So first, the context. I'm a crypto engineer at IDEMIA, that is the merge between Morpho and Aberture technologies. Our main activities are related to identity management and secure transaction. So more precisely, with my team in the Crypto and Security Labs, we developed and evaluate crypto libraries for various products based on smart card. So if for payments you use your smartphone or a bank card with a chip, or if you have a biometric passport or an electronic ID card, then you probably already have run our crypto algorithm. So our position regarding post-quantum crypto is to start the deployment right now on today's smart cards, and I'll try to explain why and what issues we are facing. So in the following slides, I will describe some constraints specific to smart cards and their impact for the transition to post-quantum crypto. So first, what is the architecture of a smart card? At high level, it's very similar to a desktop computer or a laptop. So there are two kinds of memories. The non-volatile memory, like an hard drive or a SSD. It contains persistent data, like the operating system, programs, documents. The second type is the RAM, that is the working memory. The central component is the CPU, the processor. It can read and write data from and to the different memories, and it can process this data. So the CPU is a general purpose processor, so that for very specific tasks, a dedicated hardware can be much more efficient. So for example, if you want to play video games, you may use a powerful video card, and such a card can only do very specific computations related to image processing, but it can do it much, much faster than the CPU. To interact with the machine, you use input-output devices like a keyboard, a screen, or a network interface. So the smart card architecture is pretty much the same. The differences are that all these components are together in one very tiny chip. About the dedicated hardware, it's of course not meant to play video games, but to deal with security, because this is the main purpose of a smart card. So for instance, a typical smart card has hardware to generate random numbers, to accelerate symmetric crypto, or to accelerate the modular arithmetic with large numbers. That is very useful for RSA and elliptic curve crypto. About the input-outputs, a smart card has generally a contact pad for contact payment, contact transaction, and or an antenna for contactless communications. So at high level, a smart card is similar to a computer, but in fact, its computing power is much lower. So for example, if you take a $400 desktop computer, its CPU has 4 cores running at 4 GHz, while the high-end smart card has only 1 core running at 101 MHz. Then, if you look just at the frequency, it's 40 times slower. And in addition, the computer has more cores, larger registers, and a larger instruction set, so that in fact, the smart card is even more slower than that. About the memory, a typical computer has at least 8 GB, whereas the high-end smart card has less than 50 kilobytes. So now let's compare it with a Cortex-M4 device, that is the NIST target for embedded systems. So on a smart card, we generally have a Cortex-M3 CPU that is pretty much like a Cortex-M4, where multiplications are slower. So again, if we look just at the frequency, the smart card is more than 1.6 times slower. but because of the server multiplications, it can be even worse than that. The amount of memory is 4 times less on the smart card, and we will see that this can make a huge difference with post-quantum crypto. Likewise, the communication rates are pretty slow. It's generally less than 100 kilobytes per second. And despite these poor performances, strong constraints may be required on smart card products. So, for example, a contactless banking transaction must be done in less than 300 milliseconds. We can also have constraints on key generations, because for security reasons, the key generation can be required to be done on the card in a secure factory. Hence, because this is in a factory, the slower you are, the more expensive it is, so you have to be as fast as possible. Hence, we think that it would be really hard to convince our clients to embed post-quantum crypto if the key generation takes more than 3 or 4 seconds. So, how to satisfy such constraints? First, the smart cards have dedicated hardware to perform crypto tasks. So, for example, it can generate a 32-bit random in several dozen cycles. It can encrypt or decrypt one block with AES in several hundred cycles, or compute the modular multiplication of large numbers in several thousand cycles. And in addition, these accelerators often run in parallel. So this means that during their computations, you can still use the CPU. So for example, to achieve independent tasks like preparing the next data to process or the next block to encrypt. But unfortunately, for now, on smart cards, there is no such accelerator for post-quantum crypto. So to save time, we can also perform off-card computations. For example, in Europe, a lower can sign, using a smart card, the scan of an official document. So because of the protocol, at least one part of the document has to be processed on the card. You cannot sign the hash of the entire document. So the following is done. On the computer, the document is hashed until the last block. And then the corresponding state of the hash function, that is a kind of parcel hash, and the last block of the document are sent to the card. And on the card, the hash computation is finalized and the signature is computed. So for large documents, this is much faster than sending the entire document to the card because of the slow communication rate and the low processing power of the smart card. But unfortunately, this cannot be done if the signature algorithm computes the hash of something like a random followed by the message instead of the message directly. So in addition to performance constraints, there are also strong security constraints, because unlike a computer or a server on the internet, with a smart card, the user can be the same person as the attacker. Moreover, the card issuer has no way to monitor or to take any remote action, and it's very hard to deploy patches, because it requires all the concerned cards to be connected to a specific terminal for the update, and we want to be sure that the update is genuine and is not a malware, and so on. And last but not least, smart cards are sensitive to physical attacks, like side channel and fault attacks. So to ensure a certain security level in practice, both hardware and software can be certified after evaluation by an independent lab. But this is a very long process that takes up to 18 months for the highest level. Then our development must be anticipated, and that's why we are trying to deploy post-quantum crypto right now, because there is basically an 18 months delay between the end of the development of a crypto library and the moment we can embed it into a real-life product. So on a smart card, crypto algorithms are vulnerable to physical attacks, like power analysis or correlation power analysis. So basically, by measuring the power consumption or electromagnetic radiations, you can get information about the secrets. So masking is generally the way to thwart such attacks, to decorrelate the power consumption from the secret. But then you have to process both the masked value and the mask independently, instead of only one unmasked data. Then you can expect, at best, to double the execution time and the RAM consumption. So practically, it's often worse than that. For instance, the masked version of dilithium is more than 5 times slower than the unmasked version, even though a power of 2 modulus was used to make the masking even faster. Likewise, smart cards are sensitive to fault attacks, that are attacks that perturbate either the execution or the value being processed, so that you have to add some redundancy that is also time-consuming. And if we consider other attacks like safe error or template attacks, then we have to put additional checks or shuffling. So as a consequence, the security against physical attacks can be very expensive. So unfortunately, all the previous constraints eliminate some finalists. So in this slide, the number of cycles come from the Cortex-M4 implementation for the mentioned references, and the time is the time to perform this number of cycles at 100 MHz, like on a smart card. So Mac-Ellis needs too much RAM, because even if we consider an optimized implementation, it's more than 70 kilobytes, while on a typical smart card, you have less than 50 kilobytes, and you need several kilobytes to run the operating system. And in addition, the time to generate a key pair and to output the large public key would be more than 14 seconds on a smart card. So Falcon seems to be okay without any countermeasures against physical attacks, but if we add the masking, then too much RAM would be needed, and the key generation might be too slow. Likewise, Wenbo Classic seems to be okay, but adding countermeasures and the communication time to output the large public key leads to an estimation of more than 4 seconds that may be too slow for a key generation performed in the factory. So for now, only the lattice-based finalists are practical on smart cards. Only the remaining lattice-based finalists. So to conclude, there are some ideas, some propositions to make the post-quantum crypto deployment easier on a smart card. So the first point is that if we want to deploy post-quantum crypto on smart card as soon as possible, then at least one key exchange and one signatures that fits in current smart cards should be in the future standards. In addition, it would be really great if, in addition to Cortex-M4, we could see more low memory devices in the papers, in implementation, in benchmarks, and so on. So even if we understand that it's not an easy task, it could be really great. About the dedicated hardware, it's certainly too soon for chip manufacturer to commit to the development of a coprocessor that speeds up the arithmetic of a particular schemes, but K-check coprocessor, that is the core of both SHA and shake algorithm, would be very useful, and especially if it can run in parallel, because most schemes spend between 40 and 70% of their time on hashing. So it will be a consequent improvement. If we want to be able to perform off-card hashing for qualified signatures, then we must avoid the computation of stuff like the hash of a random first followed by the message, and instead the hash of the message first eventually concatenated with other things could allow this kind of off-card pre-computation. But of course, such a modification must be done without decreasing the security, and thus we think that this point may need investigation. So my last point is about algorithm specification and parameters. So there are results on the speedup of polynomial multiplications using either existing RSA coprocessors or new generic hardware. But that doesn't work in the entity domain. Hence, for the algorithms assuming in the specification that the random vectors or random matrices are in the entity domain, conversion back from the entity domain is required to use these results. But maybe in the standards, we may include both versions. So one where the randoms are considered in the entity domain, and one where they are viewed as standard numbers. Likewise, while using entity-compatible prime modulus is generally faster for polynomial multiplication using the entity, it can be very, very painful with masking. So as suggested for dilithium, replacing the prime modulus with the power of 2 modulus is much faster for the masked version. So as a conclusion, we think that these points may be investigated in order to find some trade-off, allowing an easier transition on very constrained device like smart cards, even if it decreases a little bit the performances on other platforms. And that's it. Thank you very much for listening.
All right, thank you. We have a couple of questions on Blue Jeans and one on Slack. We don't have time to take them online, so if you could answer them in the sessions.
Yeah, okay.
All right, thank you.
Thank you.
So next we're going to hear from Derek Atkins. He's going to talk about requirements for post-quantum cryptography on embedded devices in the IoT.
Hi. For those of you who don't already know me, my name is Derek Atkins, and I'm the Chief Technology Officer of Veridify Security. Today, I'd like to discuss the requirements for post-quantum cryptography on embedded devices for the Internet of Things. I want to start out by saying the Internet of Things needs post-quantum cryptography. It needs it badly, and it probably needs it more than the regular Internet at large. And here's why. The number one reason is that the Internet of Things is made of very long-lived devices. I'm not talking just a few years or maybe even a decade. In some cases, these devices are out in the field, deployed, and running for 20 to 40 years. For example, there are devices on lampposts and controllers for lampposts that are making a mesh network for communication, and they get changed out about once every 20 years. And I'm not exaggerating that number. It could be much more than that. These devices of the Internet of Things are embedded in the critical infrastructure of things we use every day. They're in the power grid, water treatment, transportation controls, airplanes, cars, pipelines. These devices are out and being used in critical infrastructure and stuff that controls and manages our lives every day. Now with firmware updates, we can update code, fix bugs, even update methods. However, it's very, very hard to change a hardware root of trust via firmware update. One would suggest that in order to really secure a device, the security needs to be rooted in the silicon and the hardware itself, and that can't be changed by software because that would be a bug. As a result, I would suggest that we need long-lived trusted crypto now to support the Internet of Things. Now, the other thing I want to suggest is that the MCUs, the controllers that are in these devices, are smaller than they appear. I'd like to remind you that NIST has recommended that we focus on the ARM Cortex-M4 processor. Now, the ARM4 is a great processor. It's used in many devices. It's relatively small. However, the IoT uses many, many smaller processors than that. Just as a list of some of them that we've seen is the ARM Cortex-M0 and M3. There's the RISC-V family of processors. There's the ARC family of processors, the AVR family of processors, and the list goes on and on and on. All these processors are very small, many of them smaller than the M4. They have less storage, less RAM, and slower clocks. However, these devices, with using these other MCUs, they still require post-quantum security. They're still being used in devices that require security, and if we don't support them, then we're going to have an Internet of Things with no security. So how small are these devices? I would suggest that some of these devices have clock speeds as low as 8 to 24 megahertz, although some of them can go as high as 100 to 300 megahertz. But that's nowhere near the gigahertz speeds that you see in your laptops and your cell phones. The storage capabilities are also very limited. The RAM and flash size can be as low as 16 to 32 kilobytes. Runtime RAM can be as low as 4 to 16 kilobytes. Many of these devices have no floating point. So methods that are built on floating point methods can't run. They have to be re-implemented in integer math. Another limitation on these MCUs is that some of them may not even have a 32 by 32 multiplier. Some of them may have a 16 by 16. Some of them may have a 32 by 32 yields 32 high and low. Some do have a 32 by 32 yield 64. But you can't guarantee that on these processors. So when implementing them, you have to build up your math using these smaller tools. However, again, you can't rule these out because these are what's being used today. Now, keep in mind that these resources are growing. And one thing I would point out is that the ROM, the storage spaces, that's growing faster, larger than RAM. So you're getting more flash than RAM over time. So here's some actual storage capabilities for some of the devices that we are seeing in our use cases these days. So some of the things we've seen is the XMC 1100. It's a very popular board. It's based on a Cortex M0, has 64K of flash and 16K of RAM. Another system that we are using frequently is the RSL10. Has a Cortex M3 with 384K of flash and 32K of RAM. On the very small side of things we're seeing is the PIC-8, which only has 56K of flash and only 4K of RAM. Now, I'll just suggest and point out that the ROM and storage sizes can get up to 1 to 2 megabytes on the very, very large end. And also, in many of these, you can go up to a RAM size of about 64 kilobytes. But again, these sizes are much, much smaller than the megabytes, gigabytes, or terabytes that you're used to seeing on your laptops, servers, and cell phones. You might say to yourself, well, that's fine. We'll just wait until the market can use these larger processors with more space. However, that's not how it works. The financial and market pressures are keeping these smaller devices in use. So as these devices get more flash, the smaller devices that have less flash just go into more things. So they're not going away. They're not going away anytime soon. They're just being used in smaller and smaller things. And these smaller things still need security. So how are the round 3 candidates lined up here? So I'll just suggest and point out that the metrics that I'm pointing out here came from the PQM4 project on GitHub. This is the URL. And another assumption that I'm making up front is that porting these methods to an M3 or an M0 doesn't significantly impact the RAM or ROM usages. We know that the usage will change, but I'm assuming they're not going to vary significantly. And as you'll see, even if they do change a little bit, it doesn't change the results of the recommendations I come up with. So let's start with signatures. Falcon, interestingly enough, has some trade-offs you can make. So in one instance of Falcon, the code size is approximately 160 kilobytes, but the RAM usage is only 500 bytes. That's 1/2 of a kilobyte of RAM. Now you can trade off to have smaller code size. You can reduce it down to 80 kilobytes. And the trade-off is that it uses a little bit more RAM, 4 to 8 kilobytes of RAM. Now let's compare that to dilithium, which has a tiny code size relatively of 12 to 20 kilobytes. However, the RAM usage is 40 to 70 kilobytes. Now recall that I said that the maximum large size RAM you can get is 64, and often you're 32 or smaller. So dilithium is going to have a hard time fitting on many of these processors. Now on the chem size, there's lots of capabilities here. There's plenty of options that are sitting in the 5 to 10 kilobyte code size and 3 to 24 kilobytes of RAM. So I'm not going to go into a lot of details here only because there's lots of options that we've got. So based on that, what are my recommendations? My number one recommendation to NIST and everybody is to consider devices smaller than the ARM Cortex M4. As I said, the M4 is a great processor, but there's many processors that are much smaller than it that are being used. Specifically, I would suggest at least focus and allow an ARM Cortex M0 if you don't go even smaller than that. ARM Cortex M0 is being used in lots and lots and lots of devices. RISC-V is also being used, and the smaller devices are available and are being used as well. But at least allow and focus and consider the M0 when making a decision. The other major recommendation I would suggest is that you focus on smaller RAM versus smaller ROM. So when comparing methods, something that has a less RAM usage, even if it has more code size, should be picked, in my opinion. This will enable post-quantum cryptography to fit on more smaller devices because the RAM is growing slower than the ROM. So based on these metrics and these conditions, I think the market would prefer Falcon over dilithium for signatures. Because of the smaller RAM size, I think you'll get Falcon onto many more devices than dilithium because of its greater usage of RAM. In terms of chems, both Saber or Kyber fit quite well into all of these devices. But I suggest that Kyber should take a little precedence just because its numbers are a little better. But from a numbers point of view, they both could work. So those are my recommendations. I thank you for the time. And if you have any questions, feel free to reach me. Again, my name is Derek Atkins at Veridify Security. Thank you and have a great rest of the conference.
So I guess there's a few questions that are starting to come in. Maybe they can be answered within Blue Jeans and we can move on to the next talk. So next we'll be hearing from Nina Bindel on the suitability of third round signature candidates for vehicle-to-vehicle communication.
So the work that I will present today is joint work together with Sarah McCarthy, also from University of Waterloo, and IQC, and Hanif Rabari and Jeff Tvodokus from Rochester Institute of Technology in New York. And in my talk today, I will first introduce you to secure vehicle-to-vehicle communication before I present an existing testbed to test this vehicle-to-vehicle communication, explain how we integrate post-quantum algorithms in this testbed and our experimental results. Before then, finally, I show you how to use these results to analyze specific scenarios, such as in dense environments, and stating our future work. All right, so let's dive into the V2V communication. So vehicle-to-vehicle communication is a direct wireless communication to increase the situational awareness, and it's estimated that it might prevent up to 600,000 collisions per year in the US alone. Vehicle-to-vehicle communication is basically described in these two standards, while in our work and also in this talk, I will focus on the IEEE 802.11p standard. And at the core of this standard are the so-called basic safety messages. And these are messages that are broadcasted by every vehicle about 10 BSMs per second within the vehicle's transmission rate. So what kind of information is collected in this BSM? Well, every data that helps estimating or guessing what the car's next move is, such as location, time, direction, speed, but also the state of the brake and the acceleration system. So how do we add security to V2V communication? Well, of course, by adding another standard, the IEEE 1609.2 standard, which then describes secure wireless communication. And in particular, it describes how to securely transmission these messages, the cryptographic operations that are needed, and also very importantly, the certificate management. At the moment, these standards are based on elliptic curve cryptography, such as ECDSA. And as a next step, I would like to, on a high level, describe how the BSMs are transmitted securely. So let's look at the scenario. So we have two cars, a sender and a receiver, while in practice, actually both cars are sending and receiving these BSMs. But all right, so the sender has a public and a secret key, and first the car collects these data, generates the BSM, and then signs it using its secret key. Of course, it sends the BSM and also the signature, or it broadcasts the BSM and the signature, but it also broadcasts a certified public key. And now going into detail here is a little bit goes beyond what I can cover in this talk. There are different ways of communicating these certificates, and also there are different kinds of certificates. Most importantly, there are explicit or implicit certificates where the implicit certs are used to save space. But for now, for simplicity, assume we have an explicit certificate with the public key linked to a pseudonym of the sender, certified by a CA. All right. So after receiving these messages, first, of course, the public key is extracted and then used to verify the signature on the BSM message. And if the signature is valid, then it sends the BSM to the visual board, then, for example, notifies the driver of please stop the car. And as you can imagine and also seen in this figure, this notification has to come very fast to give the driver as much time as possible to react to the notification. And that means both the BSM transmission must be in milliseconds, but also that the verification must be in milliseconds. All right, so far so good. Now, researchers at the Rochester Institute of Technology implemented a wireless hardware testbed for secure V2V communications that is based on this IEEE standard, which is also open source and written in Python. And the purpose of this testbed is not to give a very efficient implementation, but to find attacks and show effectiveness of these mitigations. And the considered test scenario for this testbed are, on the one hand, of course, sender and receiver static in a lab environment, but also when the sender and receiving are moving with or without a line of sight, really in real cars on real streets. That means here we are looking at distances from 200 to 300 meters and on speeds up to 50 kilometers per hour. So when we say we added post-quantum algorithms to that, really we mean that we added the three finalists, the three signature finalists. And before we go a little bit more into that, let's see, can we already guess how V2V communication, what kind of disadvantages or threats are there, or maybe there are also benefits. So these are the numbers everyone will know at the end of the workshop, I guess. So I will not go through them in detail. But what is clear is that all the public keys are larger than the ECDSA key, and also the signature size of the lattice-based schemes, Siliphium and Falcon, are larger than the ECDSA signature. So the question is here, do we have a danger of losing BSM packages, and might that be an issue in certain scenarios, such as jammed intersection? On the other hand, Falcon and Rainbow, for example, do have a slower signing algorithm, which might also lead to disadvantages. But then remember, verification was very important. And here the two lattice-based signature schemes are actually much faster than ECDSA. So maybe there's actually another benefit in using post-quantum algorithms. Now, to get a first impression and really to focus on certain algorithms, we extended the V2 verifier using the reference implementations that are available in the library libOQS. And we just integrated them by using Python bindings. So let me stress this again. We do not claim to have a fast implementation here of any kind, but it's really to get a first step on focusing or excluding and including certain post-quantum algorithms. So, but what are our experimental results? So the scenarios that we considered at the moment are only lab scenarios. That means, of course, the sender and receiver static, but also the sender and receiver moving with a line of sight, and the sender and receiver moving without a line of sight. And future work is planned to also bring it out on the streets and test it in real cars. All right. So what are our preliminary results? So the runtimes that we measured in the testbed are not very surprising. They really reflect what we have seen earlier on the slide. And given that the Lithium and Falcon are so much faster, in doing the verification is so much faster, it looks that the two are very good candidates to replace ECDSA. Whether Rainbow is also suitable, it's hard to say from these benchmarks. To decide that, it would be useful to see how much the implementation can be optimized to the platform that is really used in the vehicles. So our table does not want to suggest that Rainbow is not suitable. It's too early at this point in time. It gets a little bit more interesting if we look at the package sizes. So you can see that we observed no package loss from Falcon and Rainbow, but unfortunately, a BSM packet size only including the BSM data and the signature using the lithium already exceeds the maximum message size that is defined in the original V2V standard. And as I said, this BSM packet size does not even include the public key. If we include the public key, then also Rainbow, due to its large key size, also exceeds the maximal message size. Now, those of you who know the standards a little bit closer say, okay, but in practice, really explicit certificates are not really used, but implicit certificates are used. In particular, the standard describes the elliptic curve Q-Venstone implicit cert, but as far as we know, this has not been constructed for post-quantum assumptions. And since the standard does also allow explicit cert for this comparison, we're using explicit cert sizes here. All right, what does that mean for analysis in certain environments, for example, dense environments? The maximum number of ECDSA verification, and this is a number given out by Qualcomm on their processor, which is used in modern for modern V2V communication, says that they can verify up to 2,500 BSMs per second. Now, Hanif and his student analyzed dense settings. For example, they analyzed the peak hour on this highway in New York and say, in this scenario, up to 3,600 BSMs per second need to be verified. And so they propose in their paper a clever algorithm to select more important messages. And the question, is that also needed for post-quantum? And definitely, from this preliminary data using the reference implementation, it looks like Rainbow is well below this threshold of 3,600. So for Rainbow, probably also some kind of selection algorithm or method must be used. While Falcon and Dilithium using their reference implementations are already well above the threshold. To really say whether V2V communication in dense environments benefits from post-quantum, we need to do a little bit more analysis. So, of course, remember Falcon's package sizes were also small enough, but still they were larger than the package size of ECDSA. And so it must be really analyzed whether this larger packet size, together with the faster verification, leads actually to that more BSMs can be verified. And so this is certainly one of the future works that we are planning. The other one I already mentioned is that we wanted to test our algorithms in real vehicles. And the last point that we are planning to look at is to see whether we can construct implicit certificates from post-quantum, or whether we can find an alternative way to communicate post-quantum certificates. So to summarize, also I think my time is up. On the one hand, we need to customize post-quantum algorithms, for example, the Rainbow implementation to these platforms. On the other hand, we need to find another way to communicate the certificates. That means we need to adapt the public key infrastructure. And last but not least, maybe we can compromise between the packet size and the practicality to include more algorithms such as Dilithium. And with that, thank you very much for your attention, and I'm happy to take questions now or later in Slack.
Okay, thank you. I believe we have a couple of minutes for questions. The first one was about Rainbow. It was noted that Rainbow has big public keys. Wouldn't that be an issue? Don't they have to be communicated to the other vehicles?
Yeah, so definitely the large public key is definitely an issue. So there are other protocols to communicate it, but definitely this is the biggest issue with Rainbow.
Okay, thank you. The next question was, given that only a short time security is needed, could it be an option to use lower parameter sets to have smaller signatures and keys? For example, the Dilithium specification also includes smaller parameter sets than 2.
So in the standard, if I'm not mistaken, they aim at 128 bits of security. So this is what we are also aiming at. Whether this might be an option to also include dilithium, yeah, it's a good point. We might take that into consideration as well.
Okay. What is correctness in the table for signatures where dilithium gets across?
All right, thank you very much. Right, with this correctness, what we mean is that due to the big message sizes, actually we could not send any messages. This is what we mean with this correctness column. And this also explains the NA in the packet loss, because actually no packet was sent.
Okay, I think we have time for one more question. What is the signature proving here, given that key infrastructure will be a hard problem? How should the vehicle react to an unsigned but critical message?
So if I understand the question correctly, this is a question about how these messages, the important messages, are selected. If that's the question, then I would like to refer the person who asked to this paper to look into how the critical messages were selected, and they propose a message, an approach there. If not, please then maybe I didn't get the question, and please ask in Slack.
Okay, the conversation can also just continue after this through the chat session. And there was one more question that's come in now, but I think we need to move on to the next speaker, so that one will have to be taken offline.
All right, thank you.
So thank you very much. So the next speaker will be Matilda Reynal. She's going to speak about an implementation of WireGuard that uses post-quantum algorithms.
Yes, thank you very much. Can you hear me well?
Yes, thank you.
Okay, thanks. So, hi everyone, my name is Mathilde. I am Delski Security, and I am very happy to be here and to welcome you to this short presentation. So today I will talk about the process behind adding quantum resistance to the WireGuard protocol, and also evaluating the performance of the resulting software. So let's dive in already and start with a quick introduction about WireGuard itself. So WireGuard is a fast and secure open source VPN solution. It is using modern cryptography and has several nice security features as listed on the slide, and overall high performance. The WireGuard protocol works in two steps, basically. So first, there is a handshake that is performed between client and server. And during this handshake, both participants authenticate to each other, and at the same time, securely exchange some key material. The derived key material is used to open a secure tunnel using symmetric key encryption and exchange the actual network data. And when using this tunnel, a client can then hide behind a server and obtain additional privacy guarantees than what exists on the internet. So the problem here is that the cryptography that is being used, as modern as it is not quantum resistant. The tunnel part can be made quantum secure by doubling the key size, as it relies on symmetric key encryption. So there's not much interest from a research point of view. Thus, in this presentation, we'll talk about how we added quantum resistance to the WireGuard's handshake. So there are already some works that offer cross-quantum handshakes for VPNs. And in this table, we report the result of works published last year that add quantum resistance to either the OpenVPN protocol or the WireGuard protocol. And as we can see in this table that we borrowed from the post-quantum WireGuard paper, the quantum resistant handshake of WireGuard is much more practical than the OpenVPN solution. And this is why we chose to continue working with this protocol specifically and use these results as baseline. Before we dive into the technical details, I think it's important to just step back and think about what do we want to achieve and what we want to evaluate. So the performance of a VPN handshake really has two dimensions. So first the computation and then the communication cost. Both are important, but one can prevail according to the setting we are in. So in some cases, a lower runtime is preferred either for convenience or to fit computationally limited resources. On the opposite, some might require solutions where the bandwidth is the feature to minimize. So it's important for every scenario to define the settings and dimensions in order to propose the best tool that there is to maximize the performance. So with this in mind, the first thing that we did was to repeat the process of the prior post-quantum WireGuard. In this case, the handshake is built around an authenticated key exchange. And the authenticated key exchange follows the Fujioka construction, which is a recipe that combines two key encapsulation mechanisms. So one of the key encapsulation mechanisms, shortened to KEM, is working with static keys and is required to be CCA secure. And the second one is working with ephemeral keys and is required to be only CPA secure. Only participants holding the correct private key can learn the internal view of the protocol and derive the correct key material, while the others can only at best guess at random. So we choose to use plain Kyber as our instantiation of the KEM used, with a security level of 3. So Kyber is a really fast finalist that is built using security-enhancing transform over a weakly secure encryption scheme. And this approach yields results that are not very competitive on the bandwidth side, but promising when looking at the runtime, especially on the client side. And we wanted to examine further our solution to find out really of how fast can we go. And to do such, we tweaked the Kyber instance working with ephemeral keys. So we start by removing the CCA transform and augment the compression of the outputs, meaning that we drop more bits. And we can do that because in practice, a negligible decapsulation failure rate can be seen as another kill compared, for example, to the possibility of a packet drop. And relaxing the requirements give us some slack to work with. And those tricks reduce the size of the outputs, boost the performance of the scheme, and actually, as a side effect, they increase the security with arguments that can be borrowed from the learning regrounding scheme. Unfortunately, because of potential attacks, we cannot apply this trick to the Kyber instance working with static keys. Indeed, there exist attacks that target the decapsulation failures and that could lead to secret key recovery, and of course, we do not want that. So as a result, for security somewhat equal, we obtain a protocol that offers improvements over the prior works regarding computational time while staying competitive regarding the bandwidth. And while we say it stays competitive regarding the bandwidth, it's because this handshake occurs every 2 minutes or so. So the 2 additional IP packets being sent really do not impact the practicality much. And as expected, the bigger improvement on the run side is affecting mostly the clients. So whereas the lower bound of 1 IP packet per message is reached for the prior post-quantum WireGuard handshake, we quickly come to the conclusion that there is no way, as aggressively as we tried, to fit our Kyber-based handshake into 2 IP packets only. So either the security level becomes too low or the failure rate drops below the acceptable rates. And we identify the bottleneck in our cases as being the size of the ciphertext of the CCA secure Kyber instance. So what we do is that we deviate from the original approach to now try to optimize the communication cost. And we study the use of the Delpino construction, which is a different authenticated key exchange recipe that replaces the primitive working with the long-term authenticated keys from a KEM to a signature scheme. We keep using our tweaked Kyber instance with the ephemeral keys and choose to work with Rainbow, DSA, that is a finalist, and stands out because of its very small signature size. The relatively large public key size of Rainbow is not a problem in our setup, as after a one-time transfer, only a hash of the key can be used during the frequent handshakes. Hence, the preprocessing is amortized pretty quickly. So the results are presented in the last line of our table. And as you can see, we achieve a very light protocol with a traffic of 1,800 bytes. So with this approach, saving like a lot of traffic comes at the cost of a few milliseconds of computational overhead, a cost that is going to be barely perceptible by the user. So to conclude, we presented two constructions that show that there is still some improvement surface for a quantum-resistant WireGuard protocol, especially when looking to optimize one dimension while staying practical in the other one. We agree that the prior post-quantum WireGuard looks like a very good compromise, but we're glad to present protocols that show some improvements in different practical settings. And we would like to nuance any comparison with the prior work, as the setups are not exactly the same. Both are run on personal laptops, but not, as I said, exactly the same. But yet our experimental results surely can help towards providing evaluations that can be used as motivation to accelerate the transition towards post-quantum alternatives. And as last words, I would like to mention that we plan to first make sure that all recent optimizations are integrated, and if not, do it, and port our implementation to the Linux kernel space, hopefully to get even better run times. So thank you very much for your attention, and if you have any question or insights, I would be happy to hear that.
Okay, thank you very much. There is one question that's come in on Slack, but we don't have time to take it online. So if you could answer that within the Slack session.
Awesome, yes.
All right, thank you.
Thank you.
So finally, we're going to have a panel session on PQC considerations for DNSSEC. Aya Schulman will be the moderator. Aya, would you like to take over?
Hi, everyone. Welcome to the panels. Our panelists are Dr. Jim Godman from Crypto4A Technologies, Russ Housley from Visual Security, Dr. Urt Kaliski, VeriSign, Victoria Risk, ISC, and Professor Douglas Sabella from University of Waterloo, and finally, Professor Dr. Roland van Rijswijk-Day, University of Twente, and Enel Labs. So quantum is just a bit quickly a statement of purpose for this panel. Quantum computers could break current public key cryptography, and there is a threat to many internet protocols, and DNSSEC is no exception to this. So the purpose of this panel is to explore DNSSEC-related considerations for post-quantum crypto-digital signature algorithm selection with intent to spur further discussion in concert with parties who define and implement DNS and DNSSEC-related standards. The targeted parties include standard-setting organizations, researchers, DNS service providers, and DNSSEC and cryptography technology providers. Some of the main considerations for the panel are the following. DNSSEC is one of the use cases for post-quantum crypto called out by NIST, but that has been relatively less studied in contrast to other protocols such as DLS. And our goal is to explore DNSSEC-specific challenges for post-quantum crypto deployment, including which post-quantum crypto-safe algorithms are suitable for DNSSEC. Another issue is interoperability with DNSSEC with internet infrastructure. And given the broad dependence on UDP for DNS exchanges, DNSSEC is not currently considered as favorable to typical sizes of signatures and keys for post-quantum signature algorithms. DNSSEC-enabled DNS responses are too large, often requiring fragmentation, and this exposes to failures and even attacks. On the other hand, DNS over TCP is often blocked by intermediate devices. And so what is expected What is the expected impact of post-quantum algorithms on DNS packet sizes, and what are the challenges that need to be considered? And finally, DNSSEC plays a central role in the internet and constitutes one of the critical internet infrastructures. Adoption of new technologies for DNSSEC requires long deployment cycles that makes algorithm stability especially important, and frequent replacement of algorithms is challenging and expensive. So that's what we will discuss. And now we start with the first question: what is the practical impact of a quantum compromise of DNSSEC? And that will be discussed by Russ and Douglas. The stage is yours.
Hi, this is Russ Housley. I'm going to start. The first thing I want to point out is that these transitions take a very long time. When I was the security area director in the IETF, we thought we could transition from SHA-1 to SHA-256 in 5 years, and we found out we were way wrong. It took 10. So we need to make sure we build in a very long transition time, and that's problematic for DNSSEC, since DNSSEC is an authentication protocol, not a non-repudiation protocol. So people are not worried about recorded old messages being broken later. We are only worried about the live one. And so that actually works against an early transition, because people aren't going to be worried about authentication until there looks like there's a quantum computer close to the horizon. And finally, there's a bunch of infrastructure that makes it difficult to use large public keys and large signatures. It's not because the DNSSEC protocol is broken in any way. It's because people tend to use it with UDP where messages are short, and firewalls and some implementations block the use of TCP, which is what would be used when the messages are long. And so we need to make sure that those firewalls and other implementation constraints are adjusted to deal with the longer signature and the longer public keys that are needed. Over to Doug.
Yeah, Russ, that's a great point that there may be less interest or less initiative for a quick transition for DNSSEC because authentication is forward-looking, but it does mean that we have more time too. We don't have to worry about retroactive decryption problems like we do with secure channel protocols. We have a bit more time to get DNSSEC ready as well. But of course, as you said, DNSSEC transitions are very slow, so we don't have a lot of time to waste. If we did break, if we had a quantum compromise of DNSSEC, for some users that would be quite problematic because they are relying on DNSSEC. But compared to many other protocols, there's a significant fraction of users that are not making use of DNSSEC. Most consumers, I think, are using just unauthenticated DNS. So for them, they would not see as much of a difference. That doesn't mean that we shouldn't want to do this, of course. And this compromise, a quantum compromise of DNSSEC, could be somewhat mitigated because there are higher level protocols that may be providing appropriate authentication guarantees in some case. If it's web traffic, then we do have the web PKI to provide a backup for that level of authentication. So it may not be entirely catastrophic right away. I'd be curious to hear what my colleagues on the panel have to say as well.
Okay, then we move to the panel now. Anyone wants to comment?
I would. While I agree that a compromise could be partially compensated by other protocols, one of the risks that I see there is that if DNSSEC is unable to transition, there is a compromise that makes it essentially insecure. That might mean that we end up in a situation where we never consider turning it back on again. And run the risk of throwing the baby away with the bathwater. So with that in mind, I think it's important that we have a solution ready to go, or possibly transition before something goes awry. And I agree with Russ that this takes a very, very long time. We've seen that with the introduction of elliptic curve algorithms in DNSSEC, and there's no reason to think it will be any better if we transition to post-quantum algorithms.
Okay, we move to next question. What characteristics should DNSSEC have in a post-quantum world? And that will be Jim and Roland. The stage is yours.
Okay, so Jim and I agreed I would kick it off. So in light of this question, we have a couple of points. So I'm going to make 3 points, and then Jim has 2 additional points. And I think the first point that I would like to make is that we need to find the right balance of burden between signers and validators. And this is also something that we discussed in the run-up to this panel. Validation happens orders of magnitude more frequently than signing, and that means that if there is a significant increase in requirements in terms of either CPU, memory, or bandwidth, that is going to affect validators much more than it is going to affect signers. Also, resolvers generally handle much more traffic than authoritative name servers in the DNS. So this scales rather poorly for them if the burden would be on their side. And a good example of where this mismatch occurs in practice is, again, elliptic curve cryptography, where validation is an order of magnitude slower than signing. This is not prohibitive for current DNSSEC, but it was actually a worry for implementers. So this was actively discussed in the DNS community when there was discussion of whether or not these algorithms should be used. And I would expect a similar discussion for PQC algorithms if there is a mismatch in the balance here. The second challenge is going to be on the wire requirements. So recently, DNSSEC implementers and operators spent a lot of time to avoid IP fragmentation, and I would like to refer to the DNS Flag Day 2020 event, where implementers and operators specifically try to ensure that DNS packets remain below the maximum packet size on the internet. And DNSSEC with post-quantum algorithms should ideally have similar characteristics. So we would want to avoid IP fragmentation for DNS messages as much as possible. Now, likely fragmentation probably cannot be avoided in all cases. If that is the case, we should favor smaller signatures to limit the need for fragmentation to just the exchanges of key material, if that is at all possible. The final consideration I'll briefly mention is, and this ties into a point that was made for the previous question, is that while, yes, DNSSEC is mostly an authentication protocol, there are theoretic use cases for non-repudiation because DNSSEC can bootstrap trust in certificates using the DNS-based authentication of named entities, aka DANE. And this is currently mostly used in the email space to invest trust in TLS certificates for the use in Start TLS and SMTPS. But in theory, you can also invest trust in keys that belong to individuals that can be used for signing and encryption, in which case suddenly you have completely different requirements. While in practice this type of use is rarely seen, maybe it is wise to actually actively avoid this kind of use because it would introduce an immediate need for hybrid signature schemes in DNSSEC. Jim, the floor is yours.
Thank you very much, Roland. Yeah, so just to continue on, I think it's safe to say that the selection of whatever potential PQC signature candidate for DNSSEC we end up going with, it's going to probably come from one of the standards that NIST is currently trying to resolve. And I think that's strictly common sense because no vendor or a consumer for that matter is going to probably want to put their trust or what limited resources they have in developing solutions for a non-standardized algorithm. Now, unfortunately, if you take a look at the current offering of finalists as well as the alternates, unfortunately, there's really only one, and that would be Falcon, that has keys or signatures that will fit within this 1232 byte limit that's typical of DNSSEC. And if we take a look at the other options, we have, and following Roland's suggestion that perhaps signature size is the metric of interest. Well, we have Rainbow and GEMS, the multivariate standards. They have very small signatures, but they have very large keys. So discuss the fragmentation side, we'd be sending 100 kilobyte plus keys, and that might prove to be daunting. Otherwise, we can look at the other candidates, and then you could look at Sphinx Plus or Picnic, and there you have the benefit of a small key size, but unfortunately the signatures get a little large, and we would have to consider fragmentation or new transport mechanisms that avoid that problem altogether. So any way we look at it, it's going to require a significant amount of engineering effort to try and make all of this work. And if past experience is any indicator, and based on Russ's experience and it's probably going to be a very slow, it's going to be long, and it's probably going to be a bit painful process to try and make this work. So what I'm thinking is, what about if we instead use this once in a lifetime opportunity, and I do hope it is a once in a lifetime, to transition into the PQC domain and these quantum safe kind of crypto algorithms, and try to re-engineer DNSSEC to really think about what we want to do in order to get some kind of new mechanisms and techniques that they don't fit the existing architecture per se, but maybe they're not so far off, but they can provide us some significant long-term benefits. Some of the concepts we might want to consider in this case, heterogeneous signatures. So the notion of using different types of signatures for different part of the authentication chain. And one I'm particularly interested in would be using hash-based signatures for the root zone. And that would allow us to leverage their 40+ years of analysis and resiliency, essentially, in order to deliver a rock-solid kind of security foundation on which to build the authentication chain. We could also look at using Merkle trees for doing very efficient zone record signing and verification. We could try to leverage some of the new techniques that are coming out from distributed key management infrastructure to try and improve the key management problem. And then lastly, we could also look at perhaps trying to put hooks in and mechanisms to allow us to have some form of cryptographic agility. If in the catastrophic case that there is a break of one of these proposed standards, we could more easily kind of fall back on an alternative. It'd be nice if that was built into the protocol. And ultimately, at the end of the day, this would be a very complex way to solve the problem. I agree on that fact. But is it really that much more complex than trying to take the existing mechanism and make it accommodate PQC signing mechanisms, kind of their quirks, and you could almost think of them as inefficiencies from a DNS perspective? At the very least, I think it's worth considering and doing a bit of serious study and effort to determine and evaluate what is the viability and suitability of these approaches in order to have a long-term benefit on the DNSSEC front. That's it. Back to you, Haya.
Yeah, so you mentioned the large DNS packets and fragmentation. Do you think that the fraction of failures because of fragmentation with DNS over UDP is lower than if DNS were over TCP? And do you think this would be different for the PQC DNSSEC? Would it be any different if PQC DNSSEC is running over TCP? And if we see that PQC over DNSSEC has less failures over TCP, then I guess that would resolve the problem with the large responses, right?
Sorry, who's the question for?
Just a comment on the large size. Does anyone from the panel want to comment?
Hi, this is Bert Kaliski. Just to echo some of what the speakers are saying, that the constraints from DNSSEC are unique. The time scales for introducing changes can be significant. And one thing to keep in mind is that there are particular properties of how DNSSEC is operated that may make it more amenable to some techniques than other use cases. For example, especially at the root and TLD, top-level domain levels, the use of the key signing keys is ceremonial. There's a script, a process that people follow. And in a context of having a ceremony around the use of a key, it's easier to manage state. So a stateful signature scheme may be more applicable in a DNSSEC context than in a general purpose context where state might easily be reset. That can lead to shorter signatures in the hash-based schemes. So considering the question, not so much as how to drop in a replacement for the existing algorithms, but how overall to make DNSSEC quantum safe using various post-quantum techniques may give some additional optimizations.
Yeah, actually, to touch on that, Bert, from the hash-based signature approach in the stateful domain, I think one of the things we'll have to do too is we'll have to discuss with NIST about some of the mechanisms that allow us to have the DR and the resiliency we're going to need in order to put these things up at the root domain, because at the moment we can't push state to another HSM, for example, right? It'd be very difficult to have that replicant waiting in the background in case something terrible happens. So these are questions we'd have to work with NIST on and resolve too.
Actually, if you're willing to have a dealer, you can break the tree among several hardware sites. So say if you had 2 sites, you could give half of the signing space to each of those 2 sites if you're willing to trust a dealer, or destroy the dealer after they do that.
So if I can just jump in and address that, Russ, unfortunately, SP 800-208 doesn't allow you to export the state from the device that created it. So yes, you could partition the state space, but unfortunately, you're not allowed to do that at the moment. So that we'd have to come to some kind of mechanism to mediate that. But I agree, you could come up with some kind of cryptographically secure technique to partition that state too, which would be really nice. Public ledgers in order to basically publish what has been dished out essentially to other machines. I mean, there's all sorts of mechanisms and tools we could try to leverage on this front.
So I'll take this opportunity to answer two questions that popped up in the Q&A. So Mathieu Guerrier asks, after DNS Flag Day 2019, a consensus was made by the DNS community to require TCP support for most DNS, even if only recommended in the standard. Are firewalls blocking TCP really a concern for the future? And this is an excellent question. So unfortunately, this is still very much a concern, even though it's 2021 and DNS should really work over TCP. In recent work that I did for the German Federal Information Security Office, which should be published later this year, we looked at roughly 65% of the DNS namespace and surveyed support for TCP on authoritative name servers. And disappointingly, up to 4% of domains have no authoritative name servers that can be reached over TCP. And that number is simply too high to be able to even consider just using TCP. Unfortunately, this is also a losing battle because there are firewalls that block TCP for DNS. There are outdated security advice notices that require this. So this is really an issue. So TCP might not be our only horse to bet on. It would be sort of a last case resort. And the second question is from Yui Blumenthal, who asks, how do you see retrieval of DNSSEC keys in the PQ world? And I guess that depends on the algorithms that we choose. As Jim commented, if we would consider Falcon, it might all just fit in regular DNS, albeit sort of creaking at the seams. If we were to choose something like Rainbow or GEMS, we would need entirely new transport mechanisms to transport key material, because the keys are so large that they don't fit into a DNS datagram, even if transported over TCP, where the limit is 64 kilobytes.
Right. So now we next question, and we'll discuss this during the audience Q&A part at the end. Thank you. So what are the implications for post-quantum crypto algorithm selection with Gort and Victoria? The stage is yours.
Thank you, Haya. So it's good questions about what do we do for the implications of the selection. And I think we agree that there's some complexity in a transition in any infrastructure to new algorithms. And I think Vicky will have some more to add on this. But the idea of a long transition with a safe fallback seems important. That thinking of this as being an infrastructure upgrade, it's important to have a reliable foundation and a base for transition perhaps to other algorithms and back. So that again draws my attention to the attractive advantages of hash-based signatures as a starting point, something to have available, something that is understood and perhaps implementable now because of the wide deployment of hash functions for other purposes. So when I think about this as a long-term type of change that would need to be introduced, and then thinking of failure cases. What happens if you do have to make a change later on down the line? Is there a fallback? Are there alternatives that should all be in circulation at the same time? And Vicky, over to you.
Okay, in thinking about the implementation, I am thinking about the implementation in the DNS software systems initially. We're going to be dependent on having a stable implementation in OpenSSL. Most of the open source DNS software systems will simply use whatever's available in OpenSSL. The implementation is more complicated if we change the OpenSSL API, which I understand is going to happen. Another thing I'd like to point out, which will be an obstacle, is IPR restrictions. That will be really a big issue for the open source implementers. Finally, it might help speed the implementation in the open source if there's funding available for the open source DNS system implementers. one of my concerns, the second step in implementing after it's in the software, is for the validators to start adding the ability to validate the new signatures. And one thing that we learned with the root key rollover was that we don't have enough data about what the capabilities are of the many, many resolver operators on the internet. So we need some researchers to investigate the adoption of validation capabilities to help manage the rollover to the new algorithms. Finally, after the validators can validate the new algorithms and signers begin signing, it's possible that the change, depending on what is selected, may impact whether or not the signers can use the very popular inline signing methods, or if in some deployments this has to be replaced with batch processing or separate signers. I'm not concerned that that change will impact or delay the deployment significantly, though. I think the next question is about the impact on existing usage and operational models. As it's been mentioned, DNS operators have already adjusted to the elliptical curve algorithms, and I'm sure they will be able to adjust to the post-quantum cryptography algorithms. One concern that I have is that this shift may accelerate the trend towards increased reliance across the DNS ecosystem on the large open resolver sites, such as Google's 8.8.8, the Quad 9 site, and Cloudflare's 1.1.1. And this is a concern because for the health of the ecosystem, it is preferable to have a wide variety of different resolvers. But these large hosted systems are typically more agile in adopting a new technology like this. So my expectation is they'll lead the way among the resolvers. Bert, did you have anything you wanted to add to this?
I think it's important to consider that so many components have to be upgraded for the introduction of a new algorithm. The hardware and software stacks, the cryptographic modules, the signers and the verifiers, and it's a large distributed system, which is part of the success of DNS. You have a protocol, publish it as a standard, anyone can implement it. It's very different than a case where an app developer is upgrading an application on the one side and a server on the other. So all of these are something that needs to be done very methodically, and that may lead to a further question about who needs to be involved in this, and the very good process that's already underway we've seen for changing keys can then be taken to the next level through that same collaborative effort.
Right. I think, as you mentioned, that there are many parties in the ecosystem. The economic incentives to adopt post-quantum cryptography also are very different across some of the members of the ecosystem. I think the economic incentives are much stronger for the signers than they are for the validators. And some of the parties actually on both sides are very limited in their financial capability to adopt new technology quickly. So that will certainly have an impact on the speed of the adoption. Overall, though, as far as the viability in the ecosystem, I think the biggest issue for the DNS will come from increased packet sizes and increased packet fragmentation. The DNS really needs to work nearly all the time, and the one thing that would cause people to abandon DNSSEC is if this causes an increased failure rate due to transmission errors. So I guess my final comment on the trade-offs, it is likely that we'll have to choose trade-offs that make this either more convenient for signers or for the validating parties. I agree with the earlier presenters that we should prioritize the convenience of the validators for two additional reasons. The signers can't switch to the new post-quantum quantum cryptography until after the validators can validate them. And in general, the economic motivation is stronger for the signers than for the validators. So I think we want to prioritize the convenience and the economic convenience as well for the validators.
Right, excellent point. Anyone on the panel has anything to add? Good, thank you, Vicky and Bert. We are moving to the last part. And the question is, how should we move forward to address the post-quantum challenge for DNSSEC? Who, what, when, and how? And that's an open discussion with all the panel members. Does anyone want to start? Douglas?
Ooh, well, I think we've identified one of the main challenges as large packet sizes and fragmentation. So I think we're going to be needing DNS operators to start addressing that even before we really think about the post-quantum algorithms, because really all of the options we have now are going to need some progress on that front. And they can start working on eDNS0 extensions for DNS to at least get up to 1,200 or hopefully larger packet sizes than that, and also resolve some of these firewall issues. So I think those are some of the first people we'll need at the table.
Yeah, this is Russ. I agree with the the firewall issues. That's certain. I think assigning the algorithm identifiers in the IETF is the easy part. It's getting the rest of it in line, and I'm certainly interested in exploring the hash-based ideas that Jim and Bert raised.
So I'd like to comment on something that is the easiest part in the IETF, because experience teaches us that these things take a long time and nothing is easy in the IETF, fortunately and unfortunately. I mean, standards need to be well considered, but sometimes it takes a very long time. As a long-term attendee of the DNSOP working group, I expect a lot of, unless we have a clear drop-in replacement, I expect quite a bit of resistance to changes to the protocol that will be required, for example, to transport larger keys. That's going to be, not that people would be against this, but it's going to be a long discussion on how to solve this in the best possible way. And that is a discussion for which we should take the time. And if we believe that that is the road to go down, we should start it sooner rather than later, because I expect that to take a lot of time. And I hope Vicky she's unmuted herself, so she's going to back me up on that as another attendee of DNSOP.
Yes, I completely agree. It's not only the amount of time it takes to get something standardized, there's a very, very long tail in the DNS of operators who update very infrequently. So the DNS is a cost center among many other cost centers for a lot of internet service providers. This is something that really has to reach all the way around the world. Not everyone is on a CDN. And as already been mentioned, we already have issues with reachability over TCP. We have issues with eDNS compatibility. The firewall issues are more of a local problem, and that's just an endemic issue, unfortunately, in networking. One thing I wanted to mention is that there will be different challenges for those operators who have connectivity problems versus those that are enormous, heavily used systems. So one of my concerns about TCP is the scalability. And I know that is something that the DNS software vendors can be working on in the background, is TCP scalability and pipelining and so on.
Actually, I have a question for Vicky, actually. So what we're seeing from the HSM perspective of the market space, we're seeing a dramatic push. This is also a very slow moving space. People don't want to change, right? The incumbents do things, but we're seeing a real push because it's a transition to a whole new type of crypto, a whole new reality in some respects. We're seeing a lot of cycles being interrupted and being updated immediately in the fronts. Do you think the DNS sees this as significant enough a concern that they might motivate themselves to move a little quicker on this, like to get that ball rolling essentially sooner rather than later?
Sorry, were you talking specifically about HSM users?
No, I was using that as an analogy. On the HSM side of the market space, that's typically quite slow moving and people are very entrenched in their ways. But we're seeing a bit of a real push because people realize this is significant and large institutions are starting to act on this, right? They're surveying their cryptographic assets and resources and stuff. There's motion on that front. You know, it's like we're turning the super tanker. I'm just curious if that same kind of motivation on, you know, from the HSM space, could we expect that similar kind of behavior on the DNS side, that they see this as being a significant problem and this would somehow motivate the action to happen sooner rather than later?
I think if there's a breakthrough on the TLS side, that will attract everybody's attention, and that will trickle down to the DNS. But obviously, if people aren't going to worry about whether or not they can access their bank if their money isn't even there anymore. So that's probably the thing that will alert people. I also think that in general, awareness of defensive defensive security is increasing pretty rapidly. Certainly here in the US, just last week, NIST had another panel on the security of the software supply chain. So,
no, absolutely agreed. Like SolarWinds, you know, not surprised, it basically brought it to the masses. You know, people I think realize just how vulnerable and susceptible we are to that kind of thing. No, absolutely agree.
Right. I have one comment to say that I think one of the things we need to consider when deploying DNSSEC, post-quantum crypto for DNSSEC, is that these algorithms are relatively new, and it can be that a few years later we will find out vulnerabilities. So we need to also consider how to, when deploying them, how can they be exchanged efficiently and quickly in case vulnerability is discovered. Okay, so now we are moving to the last part, where we are taking questions from the audience. David, are there questions from the audience?
Well, maybe while we're waiting for a couple more questions to come in, I'll highlight a couple of questions that were in the Q&A and that have had some discussion there. There are questions from Matthew Greuet and David Zhao about cryptographic algorithms or cryptographic alternatives that aren't in round 3, whether we can consider round 2 candidates like LUOV, or candidates that aren't in the system yet, like SQI sign, which have perhaps better trade-offs. And so some of the discussion there, including a statement from Daniel Apon from NIST that people should take a look at, is that perhaps the on-ramp mechanism that NIST has mentioned to solicit alternative signature schemes in an add-on process to this process might be where we can find something with a better trade-off for DNSSEC.
Yeah, maybe a comment to add to that. It's really good that there is talk of such an on-ramp mechanism, because and I added it in the Q&A as well. It's a really attractive, like the SQI sign looks like a really attractive candidate, but as long as that is not in some way blessed, you cannot rely on such an algorithm alone, because operators that there are operators out there that are bound to standards from organizations such as NIST, and they will only be able to use it once it's been officially blessed by one of the standards bodies. And for example, all of the domains signed by federal agencies likely need to comply with NIST guidance on this.
Right, and Roland, I'll add to that point the importance of getting some early experimentation, which is a good motivation for work in the IRTF. Just try to get some things on paper and in code, which then can give some feedback on what works, what fits, leading into further standardization. So it's certainly something we've been thinking about from VeriSign's perspective. What do we want to see out there in an experimental mode, and would be open to collaborating with others on some early ideas for post-quantum DNSSEC.
And actually, just to follow up on the questions, I'm very curious, and this is probably a question for another forum, but just what is the timeline of that on-ramp process? Like, how quickly will things move through that process? We have the ability to add new things, which is fantastic, but would they be delivered in a time that could be useful for this problem in particular, let's say, right? What David's proposing there. I'd be very curious to learn more about that, which I'm assuming we will over time, because it's kind of the first time that NIST really networked it and publicized it. So we'll see how it goes.
Yeah, another interesting question is the compatibility with the standards which are done in China and how this is going to influence DNSSEC development here. And what would be the implications of incompatibility?
Well, would you see a fractured internet? Would you see people going into different kind of groups, right? If I can't resolve in one, I stay in the other. Definitely interesting.
Well, sometimes they even the Chinese use forwarders, or there were cases where Europe was using forwarders in China, so this could also have implications on reachability and implications on even things like misconfigured records and caches, or even cache poisoning.
Yes.
And for instance, if resolvers do not understand signatures they give up, maybe this may have implications on connectivity for people in Europe or even the United States, because we saw that sometimes it happens that records propagate due to this use of forwarders and may have implications on reachability of different services.
I would think that it's unlikely that there is much working DNSSEC validation in China today anyway. It's only the validation that will fail. The DNS presumably will continue to work. So.
Yeah, but if we have resolvers which enforce DNSSEC validation, which when it doesn't work, they will fail, or if they do not understand signatures, they will fail. So then they will not have reachability, right? Because currently resolvers, if they see signatures that they do not understand, they do not resend the request to a different name server, which they do in case there is a timeout, for instance.
Right. I don't have any data at my fingertips, but I would expect that the validation rates inside of China are probably very low.
Okay, so our panel is coming to an end. Thank you very much to everyone for taking part. To the audience, we are going to stay here to take your questions in case anyone has questions to us or would like to discuss anything. We are in Slack and also in the chat. Thanks a lot, and looking forward to pushing DNSSEC and post-quantum DNSSEC forward.
Okay, thank you very much. That was a great panel. We saw lots of questions in the blue jeans with also responses to them. There's discussion that's starting in Slack, and I hope that discussion continues on. We're going to take a brief about 13-minute break right now, and we will start up again at 45 minutes after the hour with the final session of the day, which is going to be on candidate updates. Hope to see you then. Thank you.